Hello again and welcome back. Before we start, let's have a look at where this whole thing discussion is going, because we started to talk about linear spaces and then about subspaces and so on and so forth, but I would like to show you the map, the metro map of linear algebra, to show you what the final destination is and why we're doing these things. So we discussed about vector spaces. We said that these are things like Rn, or at least we should be thinking about them as if they were Rn. Then we talked about subspaces, which are spaces, vector spaces inside given vector spaces. We talked about the span of some vectors. The span is simply a synonym for the set of linear combinations, like the span of v1, v2 up to vm is the set of lambda 1 v1 plus lambda 2 v2 plus lambda m vm. And then we talked about linear independence. Now we'll talk about the basis of a vector space or a subspace and the dimension of the vector space. We talk about two-dimensional, three-dimensional. Now we'll define this notion properly. Then we'll talk about linear maps. Then we'll talk about the matrix rank, a super important property in linear algebra. And this property, the property of the rank of a matrix, plays an absolutely central and crucial role towards understanding and making sense of linear systems. A linear system is a thing like this: ax equals b. So we need we are paving the way actually towards understanding, making sense of linear systems. Do they have a solution? How can I find this solution? Do they have multiple solutions? Do they have perhaps no solutions at all? All these are possibilities, and to make sense of them we need the rank. To define the rank we need to define linear maps, linear independence, and so on. Linear independence, let me just refresh your memory, because it's really important that at least you remember the definition before we move on. So the plain and dry definition of linear independence is that if lambda 1 v1 that the vectors v1, v2 and so on are linearly independent, means the following thing: if lambda 1 v1 and lambda 2 v2 plus lambda 3 v3 plus lambda n, I don't want to write n, m vm is equal to 0, so if this holds, then this implies that lambda 1 is equal, lambda 2 is equal to, and so on, is equal to lambda m is equal to 0. The only way for a linear combination to give you 0 is for all of the coefficients to be 0. I don't like this definition very much. I very much prefer an explanation of what linear independence is, although it's not very rigorous. Well, it is a bit. You have these vectors, v1, v2, v3, and vm, and these vectors have a span. So what is the span of these vectors? I'm asking actually whether the span of these vectors needs all of them, all of these vectors. So is the span of v1, v2, and so on, vm, is it the same as the span of v2, v3 up to vm without v1? Do I need v1? And then I will ask, do I need v2? Or is it that? So is it the same? If it is the same, then I don't need v1. If I don't need v1, then the set of v1, v2, v3, vm is not linearly independent. To be linearly independent means that all of these vectors are essential and we need them, and we cannot take out any of them. If you take out even a single vector from this collection, the span changes. Actually, it becomes smaller. You need them there. We gave examples in the previous video where one of these vectors or more of these vectors can be redundant. If all of them are necessary, if none of them are redundant, then we say that they are linearly independent. So if someone comes to you and they tell you this set of vectors v1, v2, v3 up to vm has this property. If I take out v1, nothing changes. What does this mean? It means that v1 was redundant, which means that these vectors are not linearly independent. So this is the concept of linear independence, and we are ready actually to talk now about the concept of a basis. Check this out. V is a vector space, and suppose that the vectors v1, v2, v3 up to vn are linearly independent and they span V. The span of these vectors is equal to V. We say that these vectors form a basis of V, a basis of V. And if V has such a basis, first of all, we say that it is finite dimensional. It has a finite basis. How many elements are in the basis? 1, 2, 3, 4, up to n. It is n dimensional. The dimension of this space is V. Example, take a plane. You have, let's say, these two vectors. They are linearly independent. If you take one away, then the span changes. It becomes a line. It collapses to a line. Okay. You need both. You need both to span, as we say, to span this plane. How many vectors? 1, 2. A plane is two-dimensional. Take this three-dimensional space in which we live. How many vectors do you need to generate it, to span it? 1, 2, 3 vectors. Not necessarily these 3 vectors. You can take these 3 vectors. You can take these 3 vectors. You can take different vectors. All of these triplets are a basis of this space, and we call it three-dimensional for this reason. Also, we say a basis. Pay attention at the article a basis. This implies we don't say the basis. There is no unique basis, just a basis. Oops. Here. So an example, take our favorite vector space, which is Rn, and take these vectors. I'm not sure whether this makes much sense to you, so let me write it in a very nice and clear way. So E1 is the vector 1, 0, etc., 0. E2 is the vector 0. Now I'm putting 1 at position 1. At position 2. And so on, 0. E3 is the vector 0, 0, and I'm putting 1 at position 3. 1, and then all the rest are zeros. Then EI, the ith vector, I'm putting 1 at position I. All the rest are zeros. Now the set of these vectors, E1, E2, up to En, is a basis of Rn. In fact, it is called the standard basis. The standard basis of Rn. So if you're too lazy to think of another basis, use this one if you need a basis. But here is another example, a more interesting example, because we have vector spaces different from Rn. Like this one, take V to be the set of polynomials that have a degree up to n. What is a polynomial? Do you remember? It's a function like this, p of x. It's a function, p of x, which is like a0 plus a1 times x plus a2 times x squared. I think that's enough. This is a polynomial of degree 2. Do you want to make degree 3? That's fine. Plus a3 x to the power 3, x cubed. This is a polynomial of degree 3. Well, to be precise, not 3, up to 3. Because what if a3 is equal to 0? This is a polynomial of degree up to 3. Maximum degree is 3. If we define these elements, so p0 of x is equal to 1. p1 of x is equal to x. p2 of x is equal to x squared, and so on and so forth. If we define these elements, these, long story short, form a basis of the space of polynomials. How many are they? From P0, P1, P2 up to Pn. There's n plus 1 of them. These form a basis. Now why? Okay, I don't want to give you a proof. This is just an example. So that's all about bases of linear spaces. By the way, it is basis in plural, in singular, bases in plural. So that's all you need to know about bases and dimensions. Did I mention that? I think I didn't. The dimension of this set Pn of R, the dimension of the vector space of polynomials of degree up to n is n plus 1. The dimension is n plus 1. Why? Because I found the basis that contains n plus 1 vectors. And you'll say, what? Vectors? These are polynomials. Yes, vectors. We can call them vectors. Why are they really, so to speak, vectors? In a way they are. They live in this vector space, the space of polynomials of degree up to n. This is a vector space. I'm allowed to call them vectors, yes. And not polynomials. This is convenient actually, because you learn about functions, you learn about polynomials, matrices, and so on and so forth. But in a way, because we like to be lazy and we like to learn one thing, to have one tool for all jobs. This is the tool for all jobs. It is the notion, the concept of a vector space. So you have vectors of Rn, bring them on. You have matrices, you have polynomials, you have functions, bring them on. You will apply exactly the same methodology. The methodology in the realm of vector spaces. So what we did is that we started by saying, I have vectors. I will generalize the concept of vectors. And I will talk about vector spaces, which can be polynomials, functions, and so on. But then I also have matrices. So now the next task is to generalize the concept of a matrix. And this gives rise to the notion of a linear map. So the same way as conventional undergrad style vectors give rise to vector spaces that are more advanced, in exactly the same way conventional first year undergraduate matrices give rise, generalize to linear maps that are concepts that we will discuss now. So we generalize the concept of a vector. Can we generalize the concept of a matrix? Yes, the answer is affirmative. And let's have a look at matrices. So how do matrices behave? I have a vector x in Rn, and I have a matrix A in Rm times n, and I have an m by n matrix. If I do the multiplication A times x, I'm getting a vector in Rm. So A is like a machine to which you give vectors, and it gives you other vectors. It gives you vectors in Rn, and it gives you back vectors in Rm. How does it do that? By multiplication. So the operation AX, as we say, maps a vector x that comes at the input to a vector AX at the output. So we have a function. We can see matrices as machines, as functions. Take in, like this, what I've written here. Take in vectors in Rn and give us back vectors in Rm. They are operations like this. In goes x, out comes ax. A second observation we can do here is that this function, this black box I have there, is linear. In what sense? If I have a times a linear combination, lambda 1x1 plus lambda 2x2, then at the output I have a linear combination like lambda 1 ax1 plus lambda 2 ax2. So these are key observations. Once again, a can be seen and treated as a function. What function? A linear function from Rn, from which I'm taking an element x, towards Rm, the output of the matrix. Think of them as functions, think of them as Python functions, as MATLAB functions, as whatever you like, as machines. So we can now generalize. Look how nicely I have u and v to be vector spaces. I can talk about such a linear function. I'll give it a special name just to sound fancy. So I have a linear map from u to v. I have a function, let's call it t, from u to v. And this function is linear. It satisfies this condition. T of a linear combination is the linear combination of the t's. A linear function. Folks, simple as that. A linear function. Next, often instead of t parenthesis x, out of laziness and nothing else, we will write tx. Well, okay, that's not entirely out of laziness. There is one more reason. T of x looks like a function. Tx pertains to the notation we use with matrices, like multiplication. So we can think now of t as a matrix when we write it like that, or we can think of t as a function if we like. We can think of it as whatever we like. All right. Now, the space of linear maps from u to v is denoted as L u comma v. And for a linear map, we always have t of 0 is always equal to 0. Or as we say, it maps 0 to 0. Some very simple examples. Take this function t from a vector space u to itself. That works like this. Takes an x, doesn't do much, gives me back x. This linear map is known as the identity map. Or let's take another example, a very simple example. Take t to be a linear map from u to v that does the following very stupid thing. Takes a vector x and it always gives you back 0. This is called the 0 map. Simple as that. Whatever you give it, it gives you back 0. Another example, slightly more interesting. Take t to be a linear map that takes in a polynomial and it gives you, let's see what it gives you. It takes a polynomial p and it gives you back the derivative of p, which is another polynomial. This is a linear map. Takes a polynomial, gives you the derivative. Yes, the derivative is a linear map. This is an important moment actually. So what I'm saying here to you is that I can treat differentiation. This is differentiation, isn't it? You give it a function. I'm saying a polynomial just to keep it simple. So this is the differentiation operator, differentiation. So first of all, I just claimed that differentiation is linear. Of course it is, isn't it? Like if I put here p1 plus p2, the derivative of p1 plus p2, isn't this the derivative of p1 plus the derivative of p2? Differentiation is a linear operation. But what I'm insinuating here, and I will state it very clearly, is that I will hereafter treat differentiation as if it were a matrix. Isn't that wonderful? So I mean, I've learned two things up to now, okay? I've learned how to work with vectors and how to work with matrices. And I want to use only these two tools, vectors and matrices, to make sense of more or less all the mathematics that exists. Okay, this is an exaggeration, but I'm just trying to make a point. So I'm trying to make sense of differentiation in terms of matrices. I said I'm trying. I haven't shown you anything more involved, but we'll get there. Integration. Maybe we can try integration as well. So let's have a look at the next example. Take this function that takes in a polynomial of degree up to n and gives me back this. It gives me back the integral from 0 to 1 of this polynomial. This is a linear map. Another example. Why? Okay, you can check for yourselves. We gave the definition of a linear map. Is this a useful concept though? Can we do anything useful with linear maps? Let's find out. So first of all, one of the things we can do with linear maps is we can multiply them with numbers. The same as matrices, yes. So A times T of U is A times T of U. Pretty simple definition. What else can we do? If I have two linear maps, I can define the sum of these linear maps, which is a new linear map. How does it work? T1 plus T2 of U is of course T1 of U plus T2 of U. And what else? And I can define products of linear maps. S times T of U is what now? It is S of T of U. So I think up to now you know this as composition. Now very audaciously we call this a product. Why? Because it looks like a matrix product. That's the idea. So the matrix product can also be seen as a composition. Can it not really? Look at that. Take A to be a matrix, say in Rn times n. Take B to be another matrix in Rn times n. What is the matrix AB if you see it as a function? Well, what AB does is that AB of x is equal to A of bx. Now if you see this as multiplication, if I write it again, abx, this means that I'm multiplying b times x, I'm getting the result, which is a vector, and then I'm passing this result to a. So this is what the equation above says. ab as a whole, as an entity, if AB were a device, that would take in x and would return to me, wait, let me move this from here because you cannot see, there. If AB were a device, a machine, that would take at the input x, and what would it do? Internally, it would first do the operation, this one, b times x, then it would take this result and multiply it by a, and it would return back to me a, b, x. So matrix product is a composition. Internally, that machine computes bx, passes it to a, and it computes a times bx. So this is the product now, but the product of linear maps. These things don't need to be matrices, but they work like matrices. And the product of linear maps has these obvious properties. So T1, T2, T3, doesn't matter whether you do T1, T2 first and then T3, but the order matters. So T1 times T2, same as with matrices, is not equal to T2 times T1. The second property is that T times identity is equal to identity times T, which is equal to T. The third property is the distributive property from the right, and the last one is the distributive property from the left. So what I'm trying to say here with these four identities is that the things you can do with matrices, you can do with linear maps. Actually, the way these are written, if you look at them, like you can look at them, actually, I mean, say you can look at them and treat them as matrices. You can say T1, T2, and T3 are matrices. Or you can have a more advanced mindset and say that these are linear maps. It doesn't make much of a difference. Can we do with linear maps many of the things we can do with matrices? Yes, we can. We can add them, we can multiply them one to another, and we can multiply them by numbers. So we can do with linear maps the following things. We can add them. We can add linear maps, T1 plus T2. We can multiply them. We can multiply them by scalars. So I can do C times T, and we can multiply them together. So I can do T1 times T2. I can define the product. Of course, to define the product, the dimensions must match. And of course, to define addition, these two linear maps need to come from the same vector, need to be defined on the same vector space. From now on, so we can think of matrices as linear maps. Sometimes we say linear operators. And we can think of them as maps that work like this. You have a matrix here, but you can think of it as a machine, as a device that takes X and returns back to you AX. X is in Rn, and AX, the result, is inside Rm. It takes an element of a vector space, it gives you back an element which is in another vector space. And now, folks, I want your full attention, because I'm about to define two extremely important notions in linear algebra: the kernel and the image of the linear map. And then I will stop the recording actually, because I want you to take a break at the end of this section and go through everything again and make sure you kind of at least know the basic definitions and how they work. So a kernel, what is a kernel? The kernel of a linear map T is defined as a set. It is the set of all points U such that T of U is equal to 0. So to put it differently, the kernel of a linear map is the set of solutions of the so-called homogeneous equation Tu is equal to 0. I'll give examples afterwards. The kernel of a linear map is never empty. Why is that? Because I can always find a point that solves this equation. I can always find at least one, there might be many, but I can always find one U that solves this equation. This is of course 0. T of 0 is equal to 0. I have written this here. So 0 is always a solution of this equation. It is always an element of the kernel. What I've written here. 0 is always an element of the kernel. And additionally, you have that T is a linear map from U to V. I have written this concisely like this. T is a linear map from U to V. Like this. The kernel is inside here. The kernel of T is a subspace of the linear space U. I have it in the slide, but I wanted to emphasize this very much. So two things I want you to keep from this slide. First one is that the kernel is a subspace of U, and the second one, that the kernel is defined as the solution of the equation T of U is equal to 0. Solve this equation, all the solutions you can find define the kernel. Next one, some very, very simple examples. So if you have the identity map, the identity, let me remind you, the identity takes U, returns U. So you want to find the kernel, so you want to solve the equation IU is equal to 0. Equivalently, U is equal to 0. So here is your single solution. The kernel of the identity is just the set that contains 0. Second, I have a typo here, I must apologize. Let 0, I meant to write, let 0 be the 0 map. And then the kernel of 0 is the whole set U. Let me explain this. So I want to solve the equation 0 times U is equal to 0. The solution is pretty obvious. It doesn't matter what you will put there. Whatever U you put, you always have 0. So take whatever U you like. All the elements of the set big U are inside the kernel of the zero map. And another example, take T to be a linear map that corresponds to this matrix. How does this linear map work? Take X that is inside Rn. So the linear map T returns to you 1, 1, 1, 1 times X. And I want to find the kernel. So I want to solve the equation T times X is equal to 0. I want to solve this equation. Equivalently, T times X, I have another typo here, x1, x2, the vector x1, x2, is equal to 0. Now, if you do the matrix vector multiplication, you end up with x1 plus x2 is equal to 0 from the first line, from the first row, and x1 plus x2 is equal to 0 from the second row as well. So you end up with the same equation twice. So it means now that all of the vectors that satisfy this equation are members of the kernel. So it means that all vectors of the form c minus c, c is anything, right? Because c comma minus c satisfy, all these vectors satisfy this equation. To put it differently, these are exactly the vectors that satisfy this equation. This means now that the kernel of T is the set of all vectors of the form C minus C, all these vectors, which is the set of C times 1 minus 1, where C is a real number. Or, to put it more concisely, it is the span of 1 minus 1. And to take it a step further, this is the span of one single vector, so it's pretty clear here that the dimension of the kernel is equal to how many vectors do I need, how many linearly independent vectors do I need to define the kernel? 1. The kernel of T is one-dimensional. Another interesting example. Here, example number 3. Take U, big U, to be the following vector space. It is the vector space of all polynomials. And let T be the twice differentiation operator. This works like this. You give it, it's a machine to which you give a polynomial P, and it gives back to you the second derivative of this polynomial. Derivative and derivative again. I'm looking for the kernel. So a P is inside the kernel if T of P is equal to 0 or if the second derivative of P is equal to 0. What are those polynomials whose second derivative is equal to 0? I'll leave this to you to be convinced that what I'm telling you is true, but these are the linear polynomials. So what is the kernel? What is the kernel of T? It is equal to, I don't want to write it mathematically, it is equal to the set of all polynomials of degree 1, this set. Okay, it is not very mathematical, but I mainly want to give you a feeling of how things work here, and then you can check the handout where things are written more rigorously. So it is this set. And I have a little question here in the footnote. Can you write this as the span of a set? Think about it. And let me check something. Range. Yes. Here we are. Range. We have defined the kernel. Now it is time to define the range of T. So T is an operator that takes me from U to V. The range is the set of all possible things that my T can output, the set of all possible results. All these results, of course, are in V, yes, but V can be a very big space. V can be a very big space, but it can so happen that my T only sends the various points, like, I'll do a little sketch. This is U, and the blue one, the cyan one, is V. So I'm taking this point, and this point goes here. This point goes here. Now I'll take another point, this point up here goes here. I'll take another point, this point goes here. I'll take a fourth point, this point goes here. I'll do it a few more times. So you see what is happening here. I'm selecting various points inside U, and whatever points I select, the result is always on this line. This line is the range of my T, or you can call it the image of T. Some people say image, some people say range. These are synonyms. The range of T is a subspace of V. The range of T is never empty, of course, needless to say. It always contains 0, so the range of V always contains 0. Usually it contains more than 0, and mathematically it is defined like this. The range of T is the set of all outputs of T, all T times U, T of U, where U is taken from the input space, U, from the input vector space. It is the set of all possible outputs that the T can give me. And I say that the matrix is injective, or I say that the matrix is 1 to 1. These are synonyms. If the following thing is happening, if TU1 is equal to TU2, implies that the only way for this to happen is for U1 to be equal to U2. Again, T of U1 is equal to TU2. This can only happen if U1 is equal to U2. So, to put it a little differently, it means that I cannot find different vectors U1 and U2 such that T of U1 is equal to T of U2. I think this is one of these cases where it helps more for me not to give you an example, but to give you a counterexample. So here is a counterexample. Take T to be an operator, to be a linear map that does the following thing. It takes a polynomial. The space of all polynomials is denoted like this, so we don't have to write polynomials, and it gives me back another polynomial. And it works like this. T of the polynomial is the derivative of the polynomial. I will take now two polynomials, the polynomial P1, which is equal to 5, just a constant, and the polynomial P2, P2 of x, of course, which is equal to 7. And I will find T of P1, and I will find T of P2. T of P1 is P1 derivative, which is equal to 0. T of P2 is P2 derivative, which is equal to 0. T of P1 is equal to T of P2, but P1 and P2 are absolutely different. They're 5 and 7, but the derivatives are identical. They are both equal to 0. How can I tell whether a given linear map is injective? I will give you this criterion that is super useful. You can tell that a linear map is injective by checking the kernel. This is why we define, this is one of the main reasons why we defined the kernel. So T is 1 to 1, it has this property. If and only if the kernel of T is a set that contains nothing but 0. I think it's best if we don't give a proof now. We can give a proof together in class. Or you can try to prove this because it's very easy. You can try to prove this by yourselves to verify that this is indeed as I'm suggesting. And if you can make it, that's brilliant. If not, we can absolutely discuss together in class. An example now, I gave you a counter example. Let me give you an example. An example of a linear map that is definitely injective is the identity. So if the linear map I has the property I of u1 is equal to I of u2, then we can deduce that u1 is equal to u2. It is injective, we just showed it. As a counter example, take the zero map. If you take any different u1 and u2, then the zero map sends both to the same thing. The zero map maps them to 0, to the same thing, but they are different. So it's not injective. Another example, one more. Take a linear map that corresponds to this matrix. This is, by the way, the same matrix as the one we discussed before. 1, 1, 1, 1. So previously we saw that the kernel of this matrix is the span of this vector, of this one here. The kernel of this matrix does not satisfy this criterion. It is not 0. It contains more elements. It's a whole line. 0 is just a point. This is a whole line. So directly we can say that this linear map is not injective. And there is the concept of injectivity. There is the concept of surjectivity. A linear map, we say that a linear map is surjective, which is also known as onto, if the range of this linear map is the whole output space. It is the whole V. So T goes from U to V. Before we said that maybe it doesn't. So maybe it's like this. This is U. This is V. So maybe the different points in U, all of them are mapped to a single line or a single flat plane, but not the entire space V. If the output space coincides with the range, if the range is V, then we say that the mapping is surjective. It occupies the whole output space. It doesn't go like to concentrate on a line or a little plane. It goes and occupies all the output space. Then we say that it is surjective or onto. I think we'll stop this recording here, and next we'll talk about something that connects the kernel with the range, and we'll be one step closer to the final destination, and the final destination is understanding and making sense of linear systems, linear equations. So don't forget, hold your breath for a while more, but we'll get there. We will eventually make sense of linear equations of the form ax equals b. To do so, we need first of all to define the rank of A. And okay, we are almost there actually. Thank you very much for watching. The next thing to do now is for you to have a look at the handout. Have a look at handout number 0. Write down your equations. I've said this before. I'll say it once again. With these videos, I don't expect you to understand absolutely everything and become masters of linear algebra. I expect you to be exposed to the material. I expect you to write down your questions, and then you will join our face-to-face meetings, and you will have all the time there and space to discuss anything you like, to solve examples, to solve exercises, and this will be actually the time and space where you will fully understand and appreciate these concepts in linear algebra. Once again, thanks very much for watching, and I'll see you next week. Goodbye.